Hello everyone, welcome to my calculus lecture. In this lecture, we continue to study L'Hopital's rule. So, in my previous lecture, we discussed this example here, right? Limit of e to the negative 1 over x when x approaches, the 0 from the right side, right? Okay. But I mistakenly, copied the question incorrectly, and I started out with the limit of this function when x goes to 0. So I had to consider two separate cases, right-hand limit, which is the original example, and also left-hand limit. Okay, I just want to show you before we move on. So here, the I suspected that, right? So limit, the left hand of a limit, uh, for the reason I gave you last time, okay, by writing the function z over e to the z as z times 1 over e to the z, right? As I suspected that the limit is going to be negative infinity. Okay, so in fact, I drew the graph of z over e to the z as shown. So this is for z from negative 5 to 5, and so in this picture it shows you, right, that in fact when z goes to infinity, right, the graph approaches 0. Okay, the red line, yeah, the red curve, right? So it approaches 0. It appears to, right? Okay, so that supports the calculation we had. And also in this case, when z goes to negative infinity, right? You see that the I just restricted the domain for better looking, but if you extend it, again, the pattern is same. So, in the case, z over e to the z, the function, goes to negative infinity. So this, again, supports my, the speculation earlier, right? Okay, so in fact, this is negative infinity. So I just wanted to tell you that. Okay, so let's move to next one. So the next thing, 0 times infinity. Okay, so if f of x times g of x assumes the indeterminate form 0 times infinity at x equals a, or at x equals plus or minus infinity, right? In that case, limit of f of x times g of x when x goes to plus or minus infinity may be found by writing the function f of x and g of x as either this form, okay, f of x over 1 over g of x, or g of x over 1 over f of x. And then we apply L'Hopital's rule, because that makes this uh, way of like representing f of x times g of x will turn this into, so 0 times infinity into 0 over 0 type, or infinity over infinity type. So we can actually apply L'Hopital's rule. So here are the examples, okay? Limit of x times e to the negative x when x goes to infinity. And also we want to calculate sine of 3 times x and times cosine of 2x when x approaches 0. Okay, so we are going to calculate these examples one by one. All right, so I'm going to my notepad. I don't have enough space, so I'm going to move to next page. So example, we want to calculate this limit here. Limit x times e to the negative x, and x goes to infinity. Okay, and this equals, well, you can write this as limit. By the way, yeah, I should mention this limit is what? Infinity times, when x goes to infinity, this goes to 0, right? So infinity times 0 type, the indeterminate form, right? So we write this as a limit x goes to infinity, x over e to the x. Then what happens? This guy here is infinity over infinity type, okay, indeterminate form. So this is where you can apply L'Hopital's rule, right? So by L'Hopital, limit x goes to infinity, we take the derivative of x, that's 1, and the derivative of e to the x stays same, e to the x, and that's going to be, when x goes to infinity, e to the x goes to infinity, so that's 0. Okay, right. So that's the answer, right? So now let's move to next example. Next example is what? Limit sine 3x and cotangent 2x and x approaches 0. Okay, x approaches 0. So this is, let's take a look at it, right? So when x goes to 0, sine 3x goes to 0, and cotangent is what? Cosine over sine. Cosine over sine. So cosine 2x over sine 2x. That's gonna go to infinity. Okay, so this is it. This whole thing is 0 times infinity type indeterminate form. Okay, so what I'm going to do is this can be written as limit x goes to 0, sine 3x over, cotangent is 1 over tangent, so tangent 2x. Okay, now what? This 0 over 0 type indeterminate form, where you can apply L'Hopital's rule, right? So by L'Hopital, this is same as limit x goes to 0. Derivative of sine 3x is 3 times cosine of x, cosine of 3x, right? By chain rule over derivative of tangent 2x is 2 times secant squared 2x, again by chain rule. Okay, so 3 over 2, that's constant, comes out of limit And when x goes to 0, cosine 3x goes to 1. Secant, that's 1 over cosine, right? And so, this goes to also 1 as well, right? So this leaves the final answer 3 over 2, 3 half. In fact, this question also, you don't really need L'Hopital's rule, okay? So here, two things to remember, okay? So recall again, limit of sine x over x when x approaches 0 equals 1. And also we know the following limit, okay? So limit when x approaches 0, tangent x over x that equals 1. Where did we see this? This is the one of the examples, right, we did earlier. So we know these two limits. Using these two limits, we can also calculate this without using L'Hopital's rule. So how do we do that? So let me call it solution Q. Okay. Limit. So sine 3x times cotangent 2x is the same as sine x over tangent 2x. Okay, so this is where I start out, right? So x goes to 0. So this can be written as limit x goes to 0. So here I'm going to write, so I'm going to divide sine 3x over by 3x, and then I'm going to divide tangent to x over, so divide by 2x, and in order to retain this equality, I'll have to multiply here the numerator by 3, and here, the denominator, this whole thing, right, by 2. Okay, so that equals 3 over 2 limit x goes to 0, right, sine 3x over 3x over tangent 2x over 2x. And then when x goes to 0, the top part, the denominator goes to 1. And I'm sorry, the numerator goes to 1, the denominator goes to 1 also, using these two limits. Okay, so overall, this equals 3 over 2. Okay, that's not bad. Okay, so next thing we talk about is the indeterminate form, infinity minus infinity. Okay, right? Remember, infinity minus infinity is not 0. Okay, because infinity is not a number. All right. So if f of x minus g of x assumes the sorry, there is typo. The indeterminate form, infinity minus infinity at x equals a, or at x equals plus or minus infinity, the limit, okay, x approaches a, f of x minus g of x, or limit x goes to plus or minus infinity. Oh, here, there should be arrow, right? Another typo, right? So I'll fix that later. Anyway, so the f of x minus g of x may be found by transforming the difference into a fraction by algebraic means and applying L'Hopital's rule. Okay, right. So having said that, let us take a look at the following examples. Okay, so one by one. So the first one is the limit of cosecant x minus cotangent x when x goes to 0. And the second one is a limit of x minus ln of x when x goes to infinity. Okay, so let me get to my notepad again. Okay, so here's the first one, right? Example. Okay, so limit cosecant x minus cotangent x when x goes to 0. Okay, right. So this is, cosecant is 1 over sine. So when x goes to 0, that goes to infinity. This is cosine x over sine x, cotangent of x is, and so when x goes to 0, that goes to infinity also. So this is, this limit is infinity minus infinity type. Okay? So this equals the limit. So let us write down each one of those functions, okay? So cosine of x and cotangent of x in terms of sine and cosine. So, the 1 over cosine is, the cosecant is 1 over sine of x minus cotangent is cosine x over sine of x. So these two guys happen to have the same denominator. So you can write this as a single fraction 1 minus cosine of x over sine of x. Okay? So now what happens when x goes to 0, top part goes to, since cosine x goes to 1, so top part goes to 0, bottom part goes to 0. So this is 0 over 0 type indeterminate form where you can apply the L'Hopital's rule. So by L'Hopital, that's going to be limit x goes to 0, derivative of the numerator, that's going to be sine of x, and derivative of bottom part, that's cosine of x. So that's tangent of x, as a matter of fact, right? But you don't have to convert it to tangent though. When x goes to 0, what happens? That's 0. Okay, so that's 0. Okay, so let us move to next example. Okay, next example. Yeah, we want to calculate limit x goes to infinity x goes to infinity, x minus ln of x, right? X minus ln of x. So this one here, when x goes to infinity, that's infinity minus infinity type indeterminate form. But here, right, we have it, I mean, there's no way you can write this as like, a single fraction, okay, right? And so, the uh, previous method doesn't apply. So what do we do? When you have something like this, we can do the following. So we are going to set, okay, the function equal to y. So x minus ln of x, okay? And then, we take the exponential, okay? So e to the exponential of, this equation, so e to the y is the same as e to the x minus ln of x, okay? The reason for this is what? I mean, the exponential function is a function, right? Okay, so, they have to be the same. Okay, now this can be written as e to the x times e to the negative ln x, and so this negative sign can be brought as what is that? The exponent of x, right? So e to the ln x to the negative 1. Okay? So which is what? This thing, this part is same as the x to the power negative inverse. Okay? So all together, this equals e to the x over x. Okay? E to the x over x. Okay, so the limit. So what I'm going to do is actually, I'm going to calculate limit when x goes to infinity, e to the y. All right? So that's the limit. X goes to infinity. The one we got here is e to the x over x. So let's take a look at this. This is when x goes to infinity, you can see that that's infinity over infinity type indeterminate form where you can apply the L'Hopital's rule. So by L'Hopital, that's going to be O. By L'Hopital, that's limit x goes to infinity. Derivative of e to the x is e to the x, and derivative of x is 1. So what happens? This is going to be infinity, right? This is going to be infinity. Now, as you can clearly see from the graph of the exponential function, I drew it here, right? Okay, here it is. So you see what happens? So when e to the x goes to infinity, you see that x goes to infinity. right? X goes to infinity, and vice versa. When x goes to infinity, e to the x goes to infinity, but when e to the x goes to infinity, x goes to infinity. So in this case, we are using y variable, right? So here, uh, since y goes to infinity when e to the y goes to infinity. Okay. Um, so that's the reason. Actually, I should have written this down here, but that's okay. So, the limit. Oh no, I'm sorry. I don't have to. I don't have to write anything further. But this is going to be infinity. Okay, so this is going to be infinity. So that's the answer. All right. The reason is that y goes to infinity. Y is this guy here, right? The function. So y goes to infinity when e to the y goes to infinity. That's what we calculated, right? So this limit here is going to be infinity. So this way we can calculate the limit. I'll stop here. We have actually one more indeterminate form, okay, that we are going to discuss. So that will be discussed in my next lecture. Okay, thank you.